Hello everyone, welcome to lecture series on power system protection. Myself Rajeshwari Nananavar, working as assistant professor in the Department of Electrical and Electronic Engineering, KLS VDIT Haliyal. Today we are dealing with second module, lecture number 14. In previous lecture we discussed the two different types of distance relays, reactance relay and Moore relay. Dealing with the reactance relay, so as we discussed that this is a relay which is going to measure the reactance of the line between the 2 points where the relay is located and the point where the fault has occurred. So that distance reactance it is going to measure. It is independent of resistance of that particular distance. So because of this when we considered the construction of this, the induction cup type construction we have used, where the upper and lower poles are energized by the current quantity, as well as it is also energizing the poles which is placed at the right hand side, and the left hand side pole is energized by the current actuating quantity. So because of the interaction of these fluxes, the two torques will be produced. Okay, so the resultant torque what we had, okay, so which is going to make the relay contacts to operate. So coming to the characteristic of this reactance relay, as we have already mentioned, it is independent of the resistance. So it is, we are getting the characteristic parallel to the R axis, the line which is parallel to the R axis. Okay, so below that particular value it is going to operate, the relay is going to operate, and beyond that particular value, so the relay is not going to operate. So that is about the reactance relay what we had discussed. And we also discussed the Moore relay, the term Moore, because it is going to measure the admittance of the particular line. So admittance is nothing but the 1 over the impedance, so that is the inverse of the impedance it is going to measure, hence the term Moore relay. So when we dealing with the construction of this, again the induction cup type is used, but the one important difference is the upper, lower as well as the right hand side poles will be energized by the voltage here, whereas the left hand side pole is energized by the current. So that is the difference what we are dealing with the reactance relay as well as the Moore relay. Okay, so again the resultant, the two flux will be produced, that resultant flux, it is because of the voltage and because of the current and the spring constant. So that spring constant we are going to neglect. So when we consider the characteristic of this Moore relay, so we are going to get a circular nature which is passing through the origin. So that is about the Moore relay what we have discussed. Moving on to the today's concept, today we are dealing with the three parts: angle impedance relay, effect of arc resistance on the performance of distance relays, and finally reach of distance relays. So after this lecture, students will have a better understanding of construction, operating principle and characteristic of angle impedance relay. So what is the meaning of angle impedance, why the term angle impedance comes over here, and what is the effect of arc resistance, what is the actually meaning of arc resistance, how it is going to affect the performance of the distance relays, and finally a different types of reach of distance relay. First, meaning of reach of distance relay and the two types there in the reach of distance relay. So the different types they are going to study in today's class. As per the Bloom's taxonomy, the today's concept comes under the understanding category level L2. So we'll move on to the angle impedance relay. It is also called as a ohm relay. So it is nothing but the which is going to measure the angle of the impedance relay. So hence the term ohm relay. It is also called as a ohm relay. An angle impedance relay measures a component of the impedance of the line at the relay location. Okay, so as and where we are going to place the relay, so at that particular location it is going to measure the angle of the impedance. It is also called a ohm relay. Its characteristic on the RX diagram is shown in figure 5a, which is a straight line and is inclined to R axis at any angle. So this is that characteristic what we have, Mn, which is inclined to the R axis at any angle. So at particular angle it is going to have a inclination. So like this, for any angle we can consider. The angle impedance relay is used in conjunction with the other relays. For example, it is used to limit the area of the Moore relay on RX diagram to make it less sensitive to power surges. So in this application, the angle impedance relay is called as a blender. For various application, along with this arc impedance, we can make use of other impedances also to have the better performance of various relays. So electromechanical angle impedance relay. How the construction of this electromechanical angle impedance relay? Again, the same induction cup type construction we are using, where it will be having the 4 poles, upper pole, lower, and the right hand side as well as the left hand side. Here also the upper, lower as well as the right hand side poles are energized by the current I. So the resultant is given by K1 into I square, the flux produced, and the left hand side pole, it is energized by the voltage and produces the operating torque given by the K2 VI cos of alpha minus phi minus alpha, and minus K3, which is nothing but the constant. Okay, so for this kind of a relay, an induction cup construction is used as shown in the figure. The torque equation of the relay is given by T is equal to K1 I square because of this actuating quantity current I, minus K2 VI cos phi minus alpha because of the actuating quantity over voltage here, and minus K3 is the spring constant. In case of reactance relay, alpha is equal to 90 degree. But for an angle impedance relay, it may have any value which governs the inclination of the characteristic with respect to R axis as shown in the figure. So here, depending upon the value of this alpha, so it is going to vary. Okay, so for that purpose it is known as an angle impedance relay. Okay, so what type of an angle we are using, so depending upon that it is going to have the value. Okay, so at what angle it is, this line is going to have a inclination, so that angle we can vary. Okay, so depending upon that it is going to give the output. So below that line it is going to trip this relay, and above that it is going to block the operation of the relay, so the relay is not going to operate. So this is about the simple angle impedance relay, or in turn called as a ohm relay. Now next we'll move on to the effect of arc resistance on the performance of the distance relay. Important concept, how this arc resistance is going to hamper or affect the performance of the distance relays. Okay, so what actually the meaning of this arc resistance? If a flashover from phase to phase or a phase to ground occurs, an arc resistance is introduced into the fault path. Okay, so if there is a flashover, okay, occurs because of the phenomena, that is going to produce an arc resistance. Okay, a resistance will be introduced, a high some amount of resistance will be introduced into the path, that is known as a arc resistance. Okay, introduced into the fault path. The arc resistance is appreciable at a higher voltages. The arc resistance is added to the impedance of the line, and hence the resultant impedance which is seen by the distance relay is increased. Okay, so now the before the flashover, if there is some impedance in the system, as and when this flashover occurs, it is going to add some more resistance to that. So as and when the resistance is getting added to the path, obviously the impedance seen by the distance relays is going to be increased. Okay, so the increased impedance will be created in the system. In case of a ground faults, the resistance of the earth is also introduced into the fault path. If I consider the ground fault, that is a line to ground, double line to ground fault, so that resistance of the earth is also introduced into the system, into the fault path, so which includes resistance of the tower footing resistance, and the earth return path, etc. So earth resistance and arc resistance combined together are known as a fault resistance in case of a ground fault. Whereas in case of a phase to phase fault, the fault resistance consists of only arc resistance, as there is a no earth resistance, because in phase to phase, in a previous lecture as we have discussed, phase to phase fault means there is a no earth resistance. Okay, so it is excluding the earth point, so hence the earth resistance is not included in the phase to phase fault. Now what actually this arc resistance? Okay, arc resistance is given by Warrington formula as R arc is equal to 29 into 10 raised to 3 into L divided by I raised to 1.4. Okay, so there is a no derivation for this, you just need to remember this. Okay, so the arc resistance is given by 29K into L divided by I raised to 1.4, where this L is nothing but a length of the arc in meter in still air. Okay, so as I told you, as and when the transients occurs, okay, as and when the flashover occurs, so it is going to create a failure of the insulation, so arc is going to be introduced there. So this arc, the length of arc, okay, on the length of arc in meters in still air, okay, so that is given by the term L, and I is a fault current in amperes. The arc resistance taking into account the wind velocity and the time is given by R arc is equal to 16,300 into 1.75 S plus Vt divided by I raised to 1.4, where this S is nothing but a conductor spacing in meters, V is a wind velocity in kilometer per hour, T is a time in seconds, and Fi is a fault current in amperes. So this is the expression you need to remember for the arc resistance. Now we'll see why this how this arc resistance is going to affect the performance of the different relays. Okay, so first we'll have a effect of arc resistance on an impedance relay. Okay, so as we have already discussed the function of this impedance relay and how this arc resistance is going to affect the performance of this impedance relay. Okay, so the relay has been set to protect a line of a impedance Z1. So as we know that impedance relay, we got a circular characteristic circle, and this is a point up to Z1 it is going to protect. The up to the value of Z1, impedance Z1, the relay is going to operate, and beyond Z1 it is not going to operate. Okay, so if a fault occurs at a point F, say consider the fault has been occurred here at a location F, okay, and arc resistance R is introduced. So because of this earth fault, okay, so there is a fault at the location F, and because of this fault an arc will be introduced, okay, and that arc resistance we are measuring it as a R. Okay, so this R is introduced into the faulty path. Okay, so the relay will measure ZF plus R. Now the total impedance of the relay measured by the measured is ZF plus R. ZF is the impedance of the line up to the point F, and to that the resistance R is also introduced. If the value of the arc resistance is greater than R, okay, so if the measured value of the arc resistance which is introduced into the fault, if it is greater than this length, okay, arc resistance is greater than that, the impedance measured by the relay will be greater than the radius of the circle. Okay, so here we have taken only up to this point. If the arc resistance is measured beyond this value, so what happens, this is going beyond the circle of the impedance relay, beyond the region of protective region of the impedance relay. Okay, so if the measured impedance R is greater than the radius of the circle, and relay will fail to operate. So as and when this case happens, the relay is not going to operate. The relay will be in a not operating condition. So thus with the arc resistance R, the relay just operates. Okay, so the maximum length of the line which can be protected is a OF when the resistance R is introduced into the fault path. So arc resistance arc causes the relay to underreach. So here you need to remember the term underreach. So what is the meaning of underreach? Okay, so actually my protection zone is from O to Z1. Okay, so actually the impedance relay is, the protective region is O to Z1. Because of the fault at location F, okay, if it was a simple impedance, it is used to what we can say, trip the relay below this, because it is below the region, inside the region. Because of the presence of this arc resistance has introduced into the fault. Okay, so if this arc resistance is value is more, so the characteristic is going beyond the region, beyond the protective region. So the fault location is going beyond the protective region. So for that purpose, the relay is not going to operate. Okay, so because of this, what happens, this arc resistance is making the impedance relay to act as a underreach. Though it has a characteristic of up to Z1, operating range of up to Z1, but it is restricting its protection up to OF only. Okay, beyond F it is not going to operate. Okay, so that how it is going to make the relay to underreach. Okay, so it is going to reduce the length distance of the protective zone. Okay, so actually it is a OZ1. Okay, because of this arc resistance it is making it is only to operate for a OF. It is a underreach. Okay, so this phenomena is known as the underreach of the distance relays. Now next, effect of arc resistance on the Moore relay. So how it is going to affect the Moore relay? The characteristic angle of the relay is same as the characteristic angle phi of the line. For a fault at point F, okay, again the same Moore relay, this is a characteristic of a Moore relay what we have taken. The actual line impedance is here it should be Z1. Okay, so the actual line impedance is Z1 from here 0 to Z1. Okay, but the impedance measured by the relay is ZF plus R. So this is the impedance measured by the relay. Okay, so suppose here the fault occurs at location F, the arc resistance R will be introduced. The resultant of these two is given by ZF plus R. Okay, which is less than Z1 again. So just observe the length of ZF plus R and Z1. Again the length of a ZF plus R is less than the Z1. So this shows that arc resistance causes the Moore relay to underreach. Again the same phenomena as just now I have explained. Okay, so if it is within the region it is going to operate, if it is beyond the region it is not going to operate. Okay, so like this arc resistance introduced because of the transient or the flashover in the faulty path, it is going to reducing the distance of the relay operation. So hence it is called as a underreach. So these arc resistance causing the Moore relay to operate as a underreach. The next, effect of arc resistance on the distance relays. Okay, so combiningly how it is affecting the operation. Okay, so if I take the all the distance relays till now whatever we have discussed, that is the impedance relay, reactance relay, Moore relay. So how this is going to affect the performance? So the arc resistance affect the performance of a different types of distance relays to different extents. Figure 6c shows the characteristic of a Moore, reactance and impedance relays on the RX diagram to protect the same line. Okay, so in this figure we are showing, so this bigger circle, the circle having a larger diameter is taken as an impedance characteristic, and the which is passing through the origin it is considered as a Moore characteristic, Moore relay characteristic, and this is a parallel line to R axis is taken as a reactance relay characteristic. So the three different impedance relay distance relay characteristic we have represented in this diagram. So the larger circle is represented by the impedance, and the smaller circle passing through the origin is a characteristic of the Moore relay, and the horizontal line to the R axis or the parallel line to the R axis is given by the reactance relay characteristic. So these are the three relay characteristics already we have discussed. Now here our discussion is how this arc resistance is going to affect the performance of each and individual relay. Okay. If a fault occurs at the point F with the arc resistance R1, the Moore relay will fail to operate, but the impedance relay, reactance relay will operate. So what he says that, so here is a fault point F. So there is a fault occurs at a location F, okay, with a arc impedance of R1, arc resistance of R1. Okay, now under this condition, which all the relays which are in a operating condition. Okay, so just observe this R1 is beyond the protective zone of the Moore relay. Okay, so the Moore relay is not going to operate. Okay, whereas this R1 which is within the protective zone of the impedance relay. So impedance relay is going to operate, whereas this R1 it is less than the characteristic of the reactance relay. It is within the zone of the reactance relay characteristic. So reactance relay is also going to operate. So when the fault arc resistance is R1, impedance relay as well as reactance relays are going to operate, but Moore relay fails to operate. Correct? If the fault occurs at the point F with the arc resistance R1, the Moore relay will fail to operate, but the impedance and reactance relays will operate. If arc resistance is increased to R2, the Moore and impedance relays fail to operate, but reactance relay will operate. How it is going to operate? Again, if I increase this arc resistance from R1 to R2, okay, if the because of the severity of the arc produced, if the resistance is increased beyond R1, okay, so the new resistance value is R2. For these values, just observe, more relay, no doubt it is not going to operate. What about the impedance relay? So impedance relay, it is also beyond the region, protective zone of the impedance characteristic. So impedance relay is also not going to operate. But what about the reactance relay? It is below the characteristic range, or the below the line what we have drawn. So again these reactance relay is going to operate. Okay, so for R1 and R2, the reactance relay will operate, no doubt it is below this. So reactance relay is going to operate, but for R1, impedance relay is going to operate, whereas more relay doesn't operating. Whereas for the arc resistance R2, impedance as well as more characteristic doesn't operate. More relay doesn't operate. Okay, so hence we come to the conclusion that this shows that the more relay is most affected by the arc resistance. Okay. For both the arc values we have taken R1 and R2, mho is getting affected. So it is the most affected relay because of the arc resistance. The impedance relay is a moderately affected, because for some value it is going to operate and some value it is not going to operate. And reactance relay is the least affected by the arc resistance, as it measures only the reactance. So as I have already mentioned while explaining the reactance relay, it is independent of the resistance value. So whatever may be the arc resistance you consider, it is not going to affect the performance of the reactance relays. Okay, so it is the least affected by the arc resistance, whereas the impedance relay is a moderately affected. To some value it may affect and to some value it doesn't affect, whereas the more relay, which is mostly affected by the effect of this arc resistance. So this is how these arc resistance, in short, if I want to tell the effect of this arc resistance, it is going to make the relay operation as a underreach. Though those relays are having a capacity of protecting the line up to a certain length, because of this arc resistance it is going to reduce the protective zone length. Though they have a capacity of larger length, because of the presence of this arc resistance, the length of protection, the length of the line protection is reduced, and hence that phenomena is called as a underreach. The relays are acting as a underreach. Okay, so this is about the effect of arc resistance on the performance of a different distance relays, likely impedance relay, more relay, and the reactance relays. And next we'll move on to the another important interesting concept known as a reach of distance relays. Okay, so just now we have discussed the underreach. Okay, so what exactly the meaning of that underreach? Okay, what the actually the meaning of reach of distance relay means what? A distance relay operates when the impedance as seen by the relay is less than the preset value. So this is already we know that distance relay operates when the impedance as seen by the relay is less than the preset value. This preset impedance or the corresponding distance is called as a reach of the relay. Okay, so how much particular distance it is going to cover? Okay, so it is a maximum length of the line up to which the relay can operate, whether it is a Z0 from the center, if I consider O to Z1, okay, O to Z2, like that, it is a maximum length of the line up to which the relay can protect from the point where the relay has been located and the distance up to which the fault has been occurred. Okay, it is a maximum length of the line where the relay is going to protect the line. So distance relays have a underreach and overreaching tendencies depending upon the fault conditions. Okay, so this distance may vary, and depending upon the distance it is going to cover, so they will be classified as a underreach relays as well as the overreach relays. When distance relay fails to operate even when the fault point is within its reach, but it is at the far end of the protected line, is called as a underreach. So just now I had explained, underreach means though the relay is having a capacity of protecting the line, okay, but because of the presence of arc resistance, its protective length is reduced, and that is known as a underreach. Okay, so the main reason for underreach is the presence of arc resistance in the faults. Okay, now the tendency of a distance relay to operate even when a fault point is beyond its preset reach. the protected length is known as a overreach. So the exactly opposite overreach means what? If there is a distance is there from relay point to the fault location, beyond this fault location also the relay is operating. Okay, so that is known as a overreach. With respect to the distance speaking, okay, so if the relay is having a protective length of up to 1 kilometer, okay, it has a capacity of protecting up to length of 1 kilometer. Okay, so because of the presence of arc resistance, if it fails to protect the entire 1 kilometer, it is protecting only a 0.7 kilometer. Okay, so then such situation is called as a underreach. Okay, so the tendency of the relay, in some cases what happens, beyond 1 kilometer if the fault occurs, then also the relay is going to operate. So that tendency is known as a overreach. So beyond the fault location also the relays are operating. So that is known as a overreach of the relays. So the reason for overreach of the distance relay is the presence of DC offset in the fault current wave, because of which impedance seen by the relay is smaller than the actual impedance. So the main reason for this overreach is the presence of DC offset current. Okay, so because of the presence of these DC offset current, the impedance will be becomes less. The impedance seen by the relay is going to be less, hence it is going to increase its length. Okay, so the actual impedance of the line up to the fault point is seems to be lesser for the relay. Okay, so how actually these underreach and overreach phenomena takes place? Now let's see. Now underreach of a distance relays, how it is going to happen? The tendency of the distance relay to restrain, that is not to operate at the preset value of the impedance or a impedance less than the preset value, is known as a underreach. Okay, arc resistance causes the distance relays to underreach. So the same phenomena, the same explanation once again here we have taken. So actually the effect of arc resistance on the impedance relay, the same which is used for the explanation of underreach. So this is a impedance relay characteristic, what we have circular fashion, the 0 O to Z1, it is a protective area of the relay. Okay, so the relay has been set to protect a line of impedance Z1. If fault occurs at a F1, the arc resistance R is introduced, the relay will measure ZF plus R. Okay, so ZF is the impedance of the line up to the point F. If the value of the arc resistance is greater than R, the impedance measured by the relay will be greater than the radius of the circle and relay will fail to operate. Okay, so if there is a fault at location F and the resistance, arc resistance measured is R. Okay, so it is going to measure the impedance as a ZF plus R. So if this arc resistance value is increased, then the impedance measured by the relay will be goes beyond the radius of the circle. So the relay will fail to operate. Okay, so with the arc resistance, thus with the arc resistance R, the relay just operates. For particular value of the arc resistance R, the relay will simply operate. If it exceeds, so the maximum length of the line which can be protected is a OF. Though it has a capacity of protecting up to OZ1, but because of the presence of arc resistance, it is protecting only a up to length of OF. Okay, so protected is OF when arc resistance is R. So arc resistance R causes the relay to underreach. So this phenomena is called as a underreach. Though it has a capacity up to Z1, but it is protecting only up to point F. So because of the presence of this arc resistance. So this is called as a underreach phenomena. Okay. Now let's move on to the next one, overreach of a distance relay. Okay. How it is going to affect the performance of the distance relays? The distance relay is prone to overreach on a transient fault consisting of a DC offset. All high speed distance relays tend to see more current due to the presence of DC offset. So because of the presence of these DC offset current, okay, so the impedance seen by the relays is going to be reduced, because as the current increases, obviously the impedance is going to be reduced. So how this phenomena takes place? The RMS value of the fault current with and without DC offset is as follows. Okay, so here for first equation we'll considering with the DC offset, and the second equation represents the without DC offset. Okay, so the I is equal to square root of I AC square plus I DC square. This is for with the DC offset. and I is equal to simply IAC, the pure alternating quantity. This is for the without DC offset. Okay. So since RMS value of the fault current with the DC offset is greater than the RMS value of the pure alternating quantities, obviously this I value is more compared to this I value. Okay. So appears to be less than the actual value, and relay tends to overreach. How it is overreaching? Let's see. The impedance seen by the relay with and without DC offset are given by. Okay. So this is a Z off with offset value. With offset value V by I. What is the offset current here? V divided by square root of IAC square plus IDC square. This is with offset, and Z no off. Without offset V by I, it is simply V by IAC. That is a without offset. Okay. Now therefore Z off is less than Z no off. Okay. So the impedance with DC offset is less than impedance without DC offset. So you can have here this current value will be more. So when this current value increases automatically, so this is going to be reduced. Okay. So this Z off is obviously the less than the Z no off without offset voltage. So the transient overreach is defined as Z of M minus Z no of M divided by Z no of M. So maximum value of the impedance with offset minus maximum value of the impedance without offset divided by maximum value of the impedance without offset into 100. So this is going to give the percentage transient overreach. So this calculation we'll have later. The transient overreach increases as the system angle tan inverse x by r increases. Now this is a figure which is actually representing the overreaching phenomena. Okay. So the first transient overreach of a distance relay. So the first figure 7a, just consider here we have a transmission line, here we have the circuit breaker, and here we have the CT. Okay. So here we are measuring at this point the fault has been occurred with a no offset input current. Okay. Without DC offset. Okay. So the impedance measured between the location where the relay has been placed and where the fault happened is nothing but the J11. The impedance measured is 11 ohms. Okay. And we have taken the output of the CT as a 110 volt. Okay. So with this, figure 7 shows overreach of a distance relay located at a. The distance relay has been adjusted to reach point F is equal to 11 ohm. That is, a fault has been occurred at a point F. So the impedance measured between the relay location and the fault point is measured as a 11 ohm. So under no effect fault current as shown in the figure. The output of the VT is 100 voltage transformer is taken as a 110 volt. The fault current at F is given as F, that is a I no offset, is equal to what is the voltage? 110 volt divided by how much is the impedance measured? 11. So totally it is giving me 10 amperes. Okay. So at this point the current measured is 10 amperes without offset, without DC offset. Okay. Now suppose that the fault point F is moved to a new point F dash, that is 13.75 ohm. Now what we are doing in the second case, instead of having a 11 ohm, now we are just increasing. Okay, increasing the fault location. Instead of 11, now we have taken the impedance as 13.75. In with respect to kilometers also you consider, earlier it was 11 kilometer, now the distance has been increased to 13.75. Okay, kilometers. So the distance of the fault has been increased. Okay. Now let me check whether for this fault also is this relay is going to operate, that we need to check. Okay. So this 13.75 ohm is introduced because of the DC offset. Okay. Now suppose that the fault point F is moved to a new point F dash, that is 13.75 ohm as shown in figure 7b, and let fault current has a DC offset of 6 amperes. Okay. Now we are considering the effect of DC offset also, that is of a 6 amperes. Thus IAC, that is a pure alternating quantity, how much it is flowing? 110 divided by 13.75, which is nothing but a 8 amperes, and how much additional DC offset has been introduced? 6 amperes. Actual current is 8 amperes, but additional of 6 amperes is current. So total current, fault current, is given by square root of IAC square plus IDC square, that is square root of 8 square plus 6 square, gives me a value of 10 amperes. Therefore, Z fictitious is equal to 110 volt divided by 10 amperes, which is nothing but 11 ohms. Okay. So, actually how much impedance we have taken? 13.75. Okay, we have taken, but how much relay, how much impedance the relay is experiencing? It is again a simple 11 ohms. Okay, so since the Z fictitious due to the DC offset now equals the setting, the relay operates. Okay, so got the point. So here, though we are increasing the fault location, the distance between the relay and the fault point we have increased. Because of this, because of the presence of the DC offset current, the relay is seeing that resistance is less than the actual resistance. Actual impedance was 13.75, but the relay is experiencing that impedance as again 11 ohm itself. So since that fictitious due to the DC offset now equals the setting, that already what we have 11, so the relay operates. Though the fault point is beyond the steady state reach of the relay, but the relay operates as a fictitious impedance due to the DC offset equal the setting of the relay. So this is a case of a overreach of the relay. Though the fault point is beyond the protection, beyond the protective zone of the relay, protective zone is up to 11 ohms. It is operating even for 13.75 ohms also, because it is operating more than beyond the reach. Hence the name overreach. Okay, so the case is known as a overreach of the relay. And the percentage, how much additional percentage protection it is providing, that is given by percentage overreach. 13.75 minus 11 divided by 11 into 100 gives me 25%. So it is having a protection of additional 25%. Percentage overreach is 25%. Okay, so this is not good as far as performance as well is considered. Okay, so we need to reduce this. How? Therefore, in order to minimize the transient overreach, okay, so we have to reduce this. Okay, the percentage overreach is taken between 10% and 20%. So we need to provide, no doubt the relay is going to operate as a overreach, but there is a limitation for the overreach phenomena. Percentage overreach should be set as per the standard. So that is given by between 10% and 20%. Therefore, distance relays cannot be set 100% of the line length to provide a high speed protection to the entire line. That's why the high speed distance relays of zone 1 is adjusted to 80% to 90% of the line length. Okay, so earlier also I told you 100% line protection is not provided, it is restricted only to 80 to 90%. Okay, so the reason is we have to provide a margin of 10% to 20% is left for a transient overreach. Okay, so just now I explained the phenomena transient overreach and errors in calculations of the line impedance. Sometimes it may become wrong calculation with respect to the impedance, measurement may becomes wrong. Okay, so sometimes there may be errors in the CTs and VTs. Okay, whatever the voltage or the current ratings we have taken from the CT, there may be some errors with that. So for all these reasons we have to have a margin of 10 to 20%. Provision of 10 to 20% need to be kept as a extra. Okay, so the line length protected is only up to 80 to 90%, whereas the rest 10 to 20% is left for the transient overshoot. Just now that is a transient over reach, errors in the CTs and VTs, or the calculation error in the line impedance. For all those we have to have a margin of 10 to 20%. So this is about the overreach as well as the underreach phenomena of the relays, how it is going to act as a underreach and how it is acting as a overreach. And finally, moving on to the summary of the today's session. So today we discussed the three important concept: angle impedance relay, how it is going to measure the impedance, effect of arc resistance on the performance of distance relay. So these arc resistance are going to cause the distance relays to act as a underreach. Okay, so because of the presence of these arc resistance, when these arc resistance occur, as and when the flashovers occurs, so these arc resistance will introduced into the fault path. So this resistance also we need to count into picture. Okay, so because of these arc resistance, the total impedance measured by the relays will be becomes larger, so the protective area is going to be lesser. For that purpose, these arc relays are going to affect the distance relays to operate as a under reach relays. Whereas the reach of distance relay, again overreach as well as the underreach. In overreach, because of the presence of the DC offset current, the impedance seen by, though the distance is more, the impedance seen by the relay seems to be less. So it is going to give the protection beyond the fault location also, beyond the protective zone also. So that is called as a overreach. Very, very important concept, please do concentrate. And on this concept, in the examination you may get a question, what is angle impedance relay? Explain the operating principle and a characteristic. Explain the effect of arc resistance on the performance of distance relays. Here you need to first explain what is the meaning of arc resistance, how it is going to be introduced, and next we need to explain effect of arc resistance on impedance relay, effect of arc resistance on more relay, and effect of arc resistance on the combination of distance relay, that is arc impedance relay, more relay as well as the reactance relay. With the particular graphs you need to explain, characteristics you need to explain, and write a note on reach of distance relay. Here you need to first explain what is the meaning of reach of distance relay and the two types what we have, under reach and overreach. With a suitable example what I had given, you can have another examples also. Okay, so with that example, if you explain, it is going to be complete the answer for the question. Write a note on reach of distance relays. So this is for the today's session, and for this concept you can refer the textbook. Thank you. Have a nice day.